So hello everyone, welcome to a new video. This is a third part of on my videos on etching, which is a technique used in fabrication of devices. So in this video, I'll be discussing about dry etching. So in dry etching, I will be talking about vapor etching and plasma etching, and also about deep reactive ion etching, which is actually widely used in semiconductor fabrication, device fabrication. So yeah, let's start the video. So, dry etching can be classified into two. One is vapor etching, and other is plasma assisted etching. So, first is vapor etching. So, vapor etching means you are basically using vapors instead of if you have seen my previous two parts, like we are using chemicals to etch the material. So here, vapors are directly used in etching of the material. So, I have given two examples here. One, xenon fluoride vapor etchant is one of the widely used vapor etchant in micromachining processes. It is a highly selective vapor etchant for silicon with virtually no attacks on metal, silicon dioxide, or other materials. It gives isotropic profiles. So, isotropic means you are etching everything. So, if you have seen my part one video, you'll know about what is isotropic and anisotropic etching. So, isotropic etching means it doesn't depend on the orientation. That is whether your orientation is 100, 110, 110, or anything. It etches everything uniformly. So that is isotropic. So you can see xenon fluoride is actually a highly selective for silicon. So this is a pretty good thing. See, xenon fluoride you can actually etch only silicon with, like, if you have a top electrode on top, or like silicon dioxide things or other materials. This will only selectively etch silicon. So I would say this is a pretty good technique. So second one is HF vapor etching of oxide, which is also, so you're using HF vapor and etching your oxide. So which will be silicon oxide. So HF actually, even the chemical way of etching, wet etching, isotropic wet etching of silicon dioxide, which I had discussed in my last video. So there also you see HF was used in etching of oxide. So here also you get isotropic profiles. So the second is a plasma etching. So what is plasma etching is, there is anisotropic plasma etching gives vertical or nearly vertical side walls. That means you are using plasma. What is plasma? Plasma means it's a it's a fourth state of matter consisting of ions and electrons, right? Actually, what is causing the etching is the ions and the other reactants and gases which is in the uh, in the chamber. That is what's causing the plasma. I think the name just came because you are having plasma actually in that. So it is so actually it has a lot of electrons, and that electrons is actually bombarding other ions and then removing the and making it positive. That means kinetic energy of electrons is accelerated using an electric field, and then it hits other atoms. It removes an electron from there and makes ions, and those ions are the ones which actually help in etching. Not just ions, there are also reactive gases, and actually you can see when I go for ions are the least things that help in. They just give a directionality to your etching. So ions are actually what gives you directionality. So the other things are what is like the gas molecules inside that is assisting you in more more of the etching thing happening. So this is a plasma etching system, as you can see. So you can see there's a bottom electrode and top electrode. So basically what happens. So because of the, if we, for example, if I'm giving a negative, so most probably the substrate, this is a substrate you can see on kept on top of the bottom electrode. So if I give a negative potential in this bottom electrode and the ions are positive, this will come and hit the substrate, and it'll give a directionality to your to whatever structure you want to make. So like basically you can make structures like this shown in A, B, and ultimately this is the image, or image, actual image, where you can see uh, like straight tube-like structures, tube-like holes produced using plasma etching. So that's what happens. So basically, also I told how plasma comes inside that, right? So basically, plasma is what? Plasma is something which is produced due to your electrons going out, and because of that, when your the ion actually absorbs an electron, it will release the energy in the form of, like, if it is in the visible range, then you will plasma mostly you will see violet colors, blue colors. So like that, some colors, like different colors of plasma based on the energy released by absorbing electron. So that is how it gives you a plasma. And so you'll get high packing density of devices plausible with plasma etching. Plasma etching is a combination of chemical reactive and physical bombardment. So chemical reactive, so for example, if you're using a CEF for a gas, then the excited molecules like CF4 uh, prime are very reactive, and ion species are accelerated by RF. So ion species are giving you the and they impart energy directionality to the surface. Ions give directionality, and CFO react to the surface and etches. So that is the basic idea in plasma etching. So the species in the plasma reactor include source gas, which is the most abundant thing, and then the etch reaction products, which is which is the reaction of all the gases inside, which accounts for 10%. Then there are excited molecules, which is a few percent, and ions. See, this is the lowest amount. Like it's like one in, what is it, 10 raised to 5. So that low is the ion concentration. So with that low itself, you can induce a directionality to your structures you make. So that is just cool. And plasma etching is based on reaction product volatility. Silicon is easily etched by halogens, silicon fluorides, chlorides, and bromides. So you can, if you have actually somebody doing fabrication, then you will know that there's something called what is it, RIECL, RIEF instruments. Like they are basically based on fluorine chemistries and chlorine chemistry. So underlying idea is all plasma etching and ion bombarding, which is happening inside. So so no ion bombarding is needed for etching if the reaction are thermodynamically favored, and the role of the ion bombardment is to induce directionality. So that is it. So that's how what I've been saying from the beginning. Ions are just to induce directionality. The the chemical reactions are the main thing which is etching. And plasma etch mechanism. So a reaction that lead to bond strength stronger than silicon bond will etch silicon. Or if you want to etch anything, then the reaction bonding formed should have higher bond strength than your original thing. So for example, if I want to etch silicon oxide, so then you can see only SIF, silicon oxide bond energy is 470. Only SIF is stronger than that one. So that means you'll have to use fluorine chemistry to, or halogens like SIF4. That is how this plasma etching works, and that is the mechanism in that idea. So if I want to etch silicon, then I can use all the three, because all the three have higher bond strength than silicon. And finally, deep reactive ion etching. So this is also a part of the plasma etching mechanism. So here, this is also called Bosch process because they actually developed it. And so here, what happens is you have a mask, and then SF6 and CFC4F8. These two are the reaction molecules in the deep reactor energy. So what happens is here you're using SF6, it etches, it will give a shape like this shown in this. Then you're using C4F8 to passivate. That means after second time, if you want to etch, the etching can go in this direction. So right, so you can't say it's etching only in this direction. So this is C4F8. Once cycle goes like this, it etches, C4F8 passivates, then it again etches with SF6. Because of the passivation in the sides, what happens? Etching doesn't proceed in that direction. So like that, you're getting by different cycles of etching deposition of CF4F8, you get vertical walls. So you may ask why then how is the C4F8 getting removed from this part? Because then only you can etch further, right? Because if it is passivating in the here also, you can't etch downward. So what happens is the this site doesn't experience the ion bombardment. Only this part experience ion bombardment, and hence only this part C4F8 will get removed, and etching this on the sides passivation is still there, and hence your etching will be ultimately from many cycles of etch passivate, you will get a straight, what is it, with good aspect ratio, you will get a straight cylindrical structure downwards by etching. So ultimately it's called vertical walls you will get. So vertical structures with DRI. So with actually a DRI, they are as a good aspect ratio of 1 is to 10. 1 is to 20 also have been achieved. So what that does, that means that for if I have a opening of 1 micron, then I can have a depth of 10 micron. So that is the aspect ratio. That means, so you can see, so this is the structure. From this structure you can see, so the more the opening, the deeper it will go. So, and one more thing in this, so these are structures which you'll get ultimately after doing DRI. So you can see it's not perfectly straight walls when you zoom in a bit, because at each etching process you'll have a what to say, a half semicircle structure or like arc like structures in the walls seen here. So that will be there. That is one thing you should know. You won't get completely vertical, but it's still good enough when I would say compared to other etching processes, you can see. So DRI is pretty good. So that's all in the video. Please do share your comments about the video in the about the video, and also please do subscribe if you like the video. Yeah, and that's all. Thank you.